should start recording. Okay. So here in the large sample case, some assumptions are relaxed. So if the sample size is large, so you do not need this assumption. The population doesn't need to be normal distribution, and we do not need to know sigma. So in this case,
Over.
even you do not need to know sigma. Yes. Any question? Okay, so when n is large, you do not know the population distribution, and you also do not need to know the sigma value. You just need to know the sample standard deviation is. So you need only this information is, and if n is large. So when you will consider n as large, if the rule of thumb is n greater than 40, but this is not always true actually. In real case, this is not always true. Even for it's a smaller sample, like a smaller sample, when the sample size is less than 40, sometimes we can also use this test. It depends on the data actually. First you will fit your data, but in this course, for learning purpose, you will consider n as large when n is greater than 40. Okay. So since this is, and in this case, the test will be z-test. So since n is large, even though sigma is unknown, you are using standard deviation s, though this distribution actually doesn't follow the normal distribution, but when n is large, we can assume that it is approximately normal. Though it is not, it doesn't exactly follow the normal distribution since s is unknown. So this follows actually t distribution, but n is large, so you can use normal distribution approximation. So the rejection regions will be same as case 1. So we'll go over an example. So the US Department of Treasury claims the mean weight of quarter is 5.66 gram. So this is the mean weight of a quarter is 5.66 gram. So this is claimed by the US Department of Treasury. A simple random sampling of 50 quarters has a mean weight of 5.652 gram. So here the sample size n is 50. So this is greater than 40, right? So we can consider it as large sample size. And the standard deviation is, the S is here, sigma is not known, but the S is given, which is 0.068 gram. And the mean is 5.652 grams. The test the claim that the mean weight of quarters in circulation is 5.66 gram at level alpha equals to 0.10. So what should be the hypothesis in this case? So what is our null hypothesis in this case? And what is our alternative hypothesis? Null will be mu. Anyone? So what is the null hypothesis in this case? Yes, null is mu equal 5.66 because this is the claim, right? So we are assuming that mean is 5.66 gram, and we'll test whether it is different from this claim. So that's mean we want to test this one. We want to test whether mu is different from excuse me, so 5.66 gram. So we want to do this test. So this is our hypothesis. Now we have to conduct a hypothesis test. Since n is large, we can still use the test statistics. Z is equal x bar minus mu, and this is s over square root of n. And in this case, mu is equals to mu naught. so which is 5.66, and x bar is the sample mean, which is 5.652, and s is the standard deviation, which is 0.068, and n is the sample size, which is 50. Now you have to plug in all this number to find the value of the test statistics. So this is our test statistics. Then you will compare the test statistics with the critical value, or you can also calculate the p-value and compare with alpha value. Okay, so this is another case, case 3. This is also one sample t-test. So the hypothesis test, what we are discussing in this chapter, all are one sample hypothesis test. Hypothesis test for single population. Okay, so in this case, the assumptions are population is normally distributed. So the population should be a normal distribution. And n is small. So if n is small, then we cannot use, we can use z-test, but the formula should be x bar minus mu sigma over square root of n. So if our assumption is n is small or the population distribution is known, if the population distribution is known and it is normal distribution, then the sample size doesn't matter. So now how the test differs actually. If sigma is known, then we'll use z-test.
But you were saying something about z-test.
Yeah. So if the population distribution is normal, sigma is known, then you will use z-test. But if population is normal, then n doesn't matter. In this case, n doesn't matter. Okay. So if the population distribution is normal and n is small and sigma is unknown, then use t-test. But if n is large, then you can still use z-test. Okay. So is it clear when you will use z-test, when you will t-test? Okay, here you can see the assumption the population is normally distributed and n is small and sigma is unknown. So what is the test statistics for t-test? The test statistics is t is equal x bar minus mu s over square root of n. And here mu is mu naught. So it will be x bar minus mu naught divided by s over square root of n. And this test statistics follows t distribution with n minus 1 degrees of freedom. So the critical value will be for two-tail test, it will be t alpha over 2 n minus 1. And for one tail, it will be t alpha n minus 1 or negative t alpha n minus 1. So you can see here the rejection region for one-sided test, it is alpha. If it is upper tail, then t greater than equal t alpha n minus 1 will reject null. If it is lower tail, then if the test statistics is less than equal negative t alpha n minus 1, then we will reject the null hypothesis. And for two-tail test, when the alternative is mu is not equal mu naught, then either we'll reject null if either t is less than equal negative t alpha over 2 n minus 1 or t is greater than equal t alpha over 2 n minus 1. Or you can also use p-value approach and you will compare the p-value with alpha. So we'll discuss about this one later. So here is another example. A random sample of n is equals to 10 apartments So here we have the rents of 10 apartment. So the sample size n is equals to 10. Is it large sample or a small sample? This is a small sample, right? Yeah. Yeah, you are right. This is a small sample. Okay. So here X bar is 531.0. So this is the sample mean. This is sample standard deviation. And n is equals to 10. So here we have all this information and we have alpha is equals to 0.05. And this example actually came from previous example. And we had the also assumption that the population distribution is normal distribution. So what type of test we need to use in this case? Should we use T test or Z test? Which test we should use in this case? Yes, we should use t-test, right? Since the sample size is small, so we should, and sigma is unknown. We know the S, we do not know sigma, so we should use t-test. Okay, so we have some other options. If the data and the assumption doesn't follow the above cases, then we can also, it is possible that none of these cases are appropriate. So we discussed 3 cases, maybe none of these cases are appropriate. So in this case, we can use a test which is distribution free. So you do not need to use any distribution. This is called non-parametric test because we do not use any parameter in that case. And we are not going to cover this one in this course. And we can also use some other distribution, other families of distribution and other test statistics to do this hypothesis test. And we can also develop a bootstrap procedure. So we are not going to cover any of this in this course, okay? So we are done with the theory of from this chapter. So now we'll go over some example and we'll try to solve those problems, okay? So here is an example. A sample of yes, so we went over up to this point. So here we compared the test statistics value with the critical value to make our decision. And we can also calculate the p-value and we can compare with alpha. So in that case, we found the p-value is, so how do we compare the p-value with alpha and make our decision? So if you can calculate the p-value, so we found for that example we discussed in the last class, the test statistics was negative 1.50, and it was a one tail test. Yeah, it was a one tail test and it was lower tail test. So for the lower tail test, the p-value is probability of z less than z observed or test statistics, ZOBS. And this is called z observed or test statistics. So that's means you have to find the probability where p is the probability of z less than negative 1.50. So if you calculate this probability using calculator or using the Z table, then you will find the probability is equal 0.0668. So this is called the p-value. So p-value for this hypothesis test. So this is the p-value for this hypothesis test, which is 0.0668. Now to make decision, you will compare this p-value with the alpha value. So in this case, the alpha was 0.01. So now we'll compare this one with alpha. So here alpha is p-value is 0.0668 and alpha is 0.01. So p-value is greater than alpha, right? So we'll reject null. If you compare the p-value, you will reject null when the p-value is less than alpha. And you will fail to reject null if p-value is greater than alpha. In this case, we found the p-value is greater than alpha, so we do not reject null, or we fail to reject null. If you find p-value is smaller than alpha, then you will reject the null hypothesis. Okay, so in case of two-tailed test, you will compare the, okay, I'll discuss it later. So how do we calculate the p-value for two-tailed hypothesis test? Okay, so we have one more example here. A sample of 16 lenses used in eyeglasses yields a mean thickness of 3.05 millimeter. So the X bar is 3.05 mm. The sample size N is 16. And the standard deviation is 0.24 millimeter. So here the population standard deviation is unknown and the sample size is small, right? So the desired true average thickness of such lenses is 3.20 millimeter. So what should be our
Where's the null hypothesis?
Yeah, so now we'll determine our null hypothesis. So what is the null hypothesis in this case? So what we want to test actually here, does the data strongly suggest that the true average thickness of such lenses differs from what is desired? So we want to test whether the true average, that's mean whether mu is different from the desired average. So what is the desired average? The desired true average is 3.20, right? So we want to test whether mu is different from 3.20, right? So what is the null hypothesis then? Mu is equal mu is equal 3.20, right? Yes.
So, okay, null hypothesis.
Yeah, this is the null hypothesis and this is the alternative hypothesis. So now we have the hypothesis statement. So now we have to determine our alpha. So before doing the test, determine your alpha, so that significance level. The significance level is given here, which is 0.05. So alpha is here, which is 0.05. Now calculate the test statistics. And before calculating the test statistics, you have to determine what type of test you will be using in this case. So can we use z-test? Can we use this test here? Is z-test appropriate in this case? Anyone? No, because S is the sigma is unknown and the sample size is small. Yes, sigma not known and the N is small. Yeah, you're right. So we cannot use
The hypothesis test is when?
yeah, so
Basically,
yes. Yeah, I'm going to that point. So we cannot use this test. So that's mean we can use t-test here, right? Because S is known and the sample size is small. So we can use t-test here. So the test statistics is t is equal x bar minus mu naught divided by s over s square root of n. So
But your name writes it down.
sorry.
I want to write it down.
Yeah. So you can write it down or you can just follow it. It is here. So
Mhm.
you can just use that one. Okay.
But what is mu naught?
Mhm.
What is mu naught? Mu naught.
Mu naught is 3.20 because the general form of the null hypothesis
Now
is
what is it for?
yeah. So this actually came from here, the mu naught. And we calculate the
You
test
said
statistics under the, yeah, very good question. So we calculate the test statistics under the null hypothesis. We assume that null is true and we calculate the test statistics. So that's why we use here x bar minus mu naught instead of mu. Because for null, we consider mu is mu naught, right? So that's why we have mu naught here in this formula. Is it clear? Is
so
that
null is like 0 or what?
it's not zero. It's a notation actually. This is mu zero. So this is just a single notation. Zero is not different from mu. Like it's not separate from mu. It's together. Mu not. It's just one symbol, which represents this value. This value. Okay. This is not like mu times zero. This is actually mu not or mu zero. This is this notation. Okay. And which denote the null hypothesis. That's been the value of the null hypothesis, which is 3 point, the value of parameter in the null hypothesis, which is mu is equals to 3.20. So mu naught is 3.20. Is it clear? Okay. So if you calculate the test statistics, then finally we found the test statistics is negative 2.50. So the next thing is we have to find the critical value based on alpha. So the alpha is 0.05. Okay, so do you have any question?
No.
Okay, so I'm muting everyone. So if you have any question, you just unmute yourself and ask the question, okay? Yeah. So here the alpha is 0.05. And based on this alpha, you will find the critical value. So what is the critical value in this case? Since this is t-test, so the critical value is t, and this is two-tailed test. So it will be alpha over 2 n minus 1. The degrees of freedom is n minus 1. So here n is 16, so n minus 1 is 15. So the degrees of freedom is 15 and alpha over 2 is 0.025. You can see here the critical value. So how many critical values we will have in this case? We'll have 2 critical values because this is two-tailed test. So for each tail, we'll have 1 critical value. So that's means we'll have 2 critical value here, and both of them will be same value with different sign. So one value will be 2.131, which is with positive sign, and the other one will be negative 2.131. So here we have two critical values. One is, you can see here 2.131, and the other one is negative 2.131. Actually, it is not z, it should be t. So it is actually t alpha over 2 n minus 1, which is this one, and this one is negative t alpha over 2 n minus 1.
Wait, so,
Okay.
so alpha is is 0.05. Why?
It is given. You can, if you look at the question, you can see the significance level was given, and it was 0.05. You can see here, alpha is the significance level is 0.05. Yeah, very good question.
Uh,
So the alpha is the level of significance, which is 0.05. It was given. Okay, so the test statistics we found negative 2.50, right? So this is our test statistics. Now we'll compare the test statistics with our critical values. So we have two critical values. One is negative 2.131. The other one is 2.131. So the left side one, this value is the rejection region, and the right side of this value is the rejection region. Now you will check with where the test statistics falls. So the test statistics falls in the rejection region because this negative 2.50 is less than negative 2.131. So we reject the null hypothesis. So in this case, we reject null.
so reject null when.
Yeah, because you can see here negative 2.50 is less than negative 2.131, right? So if you look at this plot, you will see three different regions. So this is one region, this is another one, this is another one. So two of them are rejection regions since this is two-tail test. And the region in the middle is the acceptance region, or you do not reject null if your test statistics is between these two numbers. And if your test statistics is outside this region, then you will reject. And negative 2.50 is less than negative 2.131, right? So this is on the left side of this number, right? Negative 2.50.
What is started, please.
That's why we reject the null hypothesis. Okay, so you can also use the calculator, and if you use the calculator based on the results in your calculator, you can also make the decision. So what your calculator, you will have null hypothesis and alternative hypothesis and the alpha value. And is for in a step 3, you will get the test statistics, and you will also get the p-value. So if you use calculator, you will get both p-value and test statistics. So you can use either of them. So if you use test statistics, you will compare this one with the critical value. But if you use p-value, you will compare with alpha. The p-value is 0.0245 and alpha was 0.05. Now we'll compare this p-value with alpha, whether p is less than alpha or greater than alpha. So what do you think? Is p less than alpha or greater than alpha here? This is less than alpha, right? So what should be our decision in this case? Yeah, this is less than alpha. So what should be our decision? If p is less than, we'll reject H0. Okay. So actually, why do we reject H0 when p is less than alpha? There is reason. I'm explaining a little bit. So for example, if our test is like this, mu is equals to mu naught, and alternative is mu greater than mu naught. So this is one tail test, right? So this is our Z or T alpha, whatever it is. This, for example, this is Z alpha. So this is our rejection region. Okay, then you will calculate the test statistics. Z observed or Z test. You will calculate this one, x bar minus mu naught sigma over square root of n. Okay. So what is the area of this region? Can anyone tell me what is the area of this region? So what is the area of this part, the shaded region? Anyone? How do we calculate Z alpha? Based on the area alpha, right? So what is the area of this region?
Did you say this was a one-tailed test?
Yeah, the area of this part is 1 minus alpha. The area of this part is alpha.
No, but I mean, is this a one-tailed test?
Yeah, this is one tail test. This is upper tail test. If you look at the alternative, you can see mu is greater than mu naught. Yeah, this is one tail test.
So one-tailed test is what exactly? Well, what are the types of tests? This test, one-tailed test.
The test statistics are same for one tail, two tail, and upper tail, lower tail, and two tail. Test statistics are same. The difference
Is
is
it test statistics?
the rejection region. The rejection region are different for different tests. Okay, different tail test. For left tail test.
Where's the test? Where's the tail test statistics?
Sorry.
Where's the tail test statistics?
Okay, so two tail test, the test statistics for two tail test will be also the same, exactly the same thing. The difference is the rejection region.
Yeah, but like, what are tail tests like in general? What are they for? One tail, two tail, three tail. What are they for?
Okay, so the difference, yeah. Okay, so if you remember from the last class, so we discussed all three type of test. If the alternative is greater than, this is upper tail. If the alternative is less than, this is lower tail. If in the alternative you have this sign that's not equal, then it is two tail. Not equal means it could be less than, it could be greater than, right? It is not equal.
Okay.
So it could be less, it could be more. So that's mean you have two tail in this case. Okay. Okay, so here, this is the alpha, the area of the rejection region. Okay. So now think about this. If your test statistics, Z observed, this test statistics, if it falls here, if it is somewhere here, this test statistics, then what is the probability of Z greater than Z observed? It is greater than alpha or less than alpha. If this Z observed is somewhere here, so what do you think? If you calculate the probability Z greater than, that's mean the area on the right side of Z observed. So this area is alpha. So if Z observed is somewhere here, so what will be the area, or what will be the probability for this one? Is it greater than alpha or less than alpha? Anyone? So can anyone tell me? So what will be the probability of Z greater than Z observed? Is it less than alpha or greater than alpha? Let's compare the area with alpha. This area is alpha, and we the probability of Z greater than Z observed is this area. So it is clearly greater than alpha, right? Yes, this is greater than alpha. Now we can compare. You can see Z observed is in, if it is somewhere here, then we fail to reject, right? Because this is not the rejection region. Rejection region is this part. So if your Z observed is somewhere here, then you can see the p-value or the probability is greater than alpha. It's always larger than alpha, right? But if your Z observed is somewhere here, so if suppose if Z observed is here, then the area, the probability will be this area, right? This area. So this probability is less than alpha, right? So now you can see when Z observed in the rejection region, the p-value is less than alpha. That's why we reject null when p-value is less than alpha. But if Z observed in the non-rejection region, that means it's outside the rejection region, then the p-value is greater than alpha. So that's why we fail to reject when p-value is greater than alpha. So is it clear? Why do we reject null when p-value is less than alpha? And why do we fail to reject null when p-value is greater than alpha? So if you understand this, then even you do not need to memorize it, like when you will reject and when you will fail to reject. Is it clear, or do you have any question? Okay, so here the p-value is 0.0245, which is less than alpha. So we'll reject the null hypothesis. And we also had the same decision based on critical value. So we rejected the null based on the critical value, and based on p-value, we also rejected null. Actually, we will always have the same decision of whether you will use the critical value approach or p-value approach. It doesn't matter. But if you use the p-value approach, then you will have some more information. And even if you use the confidence interval, then the confidence interval is for better because you will also have the range of the value of parameter. That means you will have one more information if you use the confidence interval to make your decision. Okay, so till now we discussed about hypothesis test for one population mean or one sample mean. So now we'll discuss about the hypothesis test for one sample proportion. For example, if we want to compare the population proportion, then you have to do a hypothesis test for one sample proportion. So what is the test statistics for one sample proportion? The parameter is P, which is proportion, and the hypothesis in this case is P is equals to P naught, and alternative will be either P is greater than P naught or P is less than P naught or P is not equal to P naught. It's also similar to the population mean. The difference is the test statistics. So in this case, if you use the Z test, then the test statistics will be Z is equal P hat, that's with the sample proportion, minus P naught, the proportion under null hypothesis, over a square root of P naught times 1 minus P naught over N. That's with the standard deviation for P hat. Okay, so this is the test statistics. Or if you use if the sample size is small, and then you can also use the t-test. Okay, so we have one example for testing the population proportion. A manufacturer of nickel hydrogen batteries randomly selects 100 nickel plates for test cells. So here the sample size is 100. Okay, so determines that 14 of the plates have blistered. So we are interested about what proportion of the plates have blistered. So that's mean here the success is if the plates has blistered. Okay, so 14 plates have blistered, so that's mean here the number of success is 14. So X is 14. So P hat is the proportion of success. So that's with X over N. So which is 14 over 100. So that's been 0.14. So this is our P hat. So now we want to do a hypothesis test with a level of significance of 10%. So alpha is, sorry, no, So does the data provide compelling evidence for concluding that more than 10%? So we want to test whether more than 10% of the players blister under such circumstances. So that's mean we want to test whether the proportion P is greater than equal 0.01 or not. So we want to test whether P is greater than 0.10. So the null hypothesis will be P is equals to 0.10. So this is our null. So here you can see the null is P is equal 0.10. The alternative is P
But
greater than.
why do you want to test if P is greater than 0.10 in the first place?
Okay, so here you can see, does the data provide compelling evidence for concluding that more than 10%? So that's mean the proportion, we want to test whether the proportion is greater than 10% or not. So that's why the alternative is P greater than 0.10. Is it clear?
Yes.
Okay. So the alpha is the level of significance. So it is given that use a level of significance 0.05. So the level of significance is 0.05. So now we will calculate the test statistics. So since this is test about a single proportion, so the test statistics will be Z is equals to P hat minus P0 over square root of P naught minus, sorry, times 1 minus P naught divided by N. So this is the test statistics for proportion. So now we'll plug in all the values. The P hat is 0.14. The P0 is 0.10. So P hat is 0.14. P naught is 0.10. And the sample size N is 100. So N is equals to 100. So now we'll plug in all the values here and it will calculate the test statistics. The test statistics is 1.33. Okay, so now we'll find the critical value. So the critical value based on the alpha. So since this is upper tail test, the critical value will be just Z alpha. So that's mean Z 0.05. So which is 1.645.
Right. So it's upper tail because it's going to almost calculate more than 0.10. It's
Sorry.
upper tail test because P is greater than 0.10.
Yeah, P naught is 0.10.
Wait, so is that why it's upper? Well, why is it upper tail test again to confirm?
So which one?
I was like, why is this particular hypothesis test an upper tail test?
Oh, okay. So you will determine the tail based on your alternative. So you will always determine the tail based on the alternative. Look at your alternative.
Okay.
So what do you see here? P
P
is
greater than
right?
0.10.
Yeah, this symbol.
Hmm.
Yeah, that's why it is upper tail test. Yeah. Okay, so since this is upper tail test, so you will check whether, I'm sorry. Okay, so since this is upper tail test, this is our Z alpha, which is 1.645. Okay, so now we'll check where the test statistics falls. Test statistics is 1.33. So it is somewhere here, right? 1.33. So is it in the rejection region or outside the rejection region? So is the test statistics outside the rejection region or inside the rejection region? Yes, this is okay. So is it inside? So I got one answer that so how about others? Do you think that it is inside the rejection region? Yes, this is outside, not inside. Yeah.
Where did you get 1.33 from again?
Okay, so we calculated the test statistics. You can see here, the test statistics is here. If you plug in all the numbers here, then you will find this is 1.33. Okay. If you simplify this one, you will get this number. Okay, so this region is the rejection region, the shaded region, this one. 1.33 is not in the shaded region. It is outside the shaded region, right? So that's mean this is not in
How did
the,
you get 1.645? Sorry.
so this is the critical value. Based on your alpha, you will find this one from the table, or you can also use the calculator. So you can use the Z table or you can use calculator. So this is the area 0.05. So for standard normal distribution, the area is 0.05, this area. Now find the value of Z. That is your critical value. So which is 1.645. Okay. So you can use the table or you can use calculator to get this number.
But how do you use calculator to get it?
Okay, so you can use TI if you use the TI calculator. Okay, then in the previous, I think it is in the previous lecture in chapter 7, yeah, you will find the instruction how to use TI calculator to get Z alpha, or you can just Google it. Okay, you can just Google it like how to find the critical value by using TI calculator. Or if you or I can also post some YouTube videos on Blackboard regarding this. Okay, yeah. Okay, so the critical value is 1.645 and the test statistics is 1.33. So since the test statistics is outside the rejection region, so we will fail to reject the null. So we do not reject the null hypothesis. So the conclusion will be we do not have sufficient evidence that the proportion is more than 10%. Okay. So if you use the calculator, you will also get the p-value. So the p-value is 0.091 and the alpha is 0.05. So that's means the p-value is greater than alpha. So you fail to reject null. Okay, so now we'll go over some more examples. So here we have the comparisons of p-value and alpha value. So now you will make the decision based on alpha and p-value. So what should be the answer for A? So pairs of p-values and significance levels alpha are given. So you have the p-values, you have alpha. For each pair, state whether the observed p-value would lead to reject the null at the given significance level. So you will make your decision whether you will reject the null hypothesis or fail to reject the null hypothesis. So here the p-value is 0.053, the alpha is 0.05. So should we reject the null or fail to reject the null in this case? So what do you think? Should we reject the null or fail to reject the null? Yes, I got two answers, two responses, and both of them are reject. Okay, so before making decision, think about this. So when do we reject null? When p-value is smaller than alpha, right? Do you think that p-value is less than alpha? So if p-value is less than alpha, you will reject. If p-value is not less than alpha, you do not reject or fail to reject. So what do you think? So should we reject or fail to reject? Yes, we fail to reject. We do not reject for part A. How about part B? Should we reject or fail to reject? Yes, part B, we reject the null hypothesis because alpha is less than, sorry, p-value is less than alpha. So this is fail to reject. This is reject. FTR means fail to reject null. So how about C, part C? Yes, FTR. So how about part D? Part D, be careful. Alpha is not 0.01. This is 0.10, right? Yeah, so we reject. So how about part E? Should I reject or fail to reject? Yes, this is FTR.
Why do you feel to reject?
Because 0.015, right? P-value is greater than alpha, right?
Yeah.
Yeah, so we fail to reject. So how about part F? Should we reject or fail to reject?
Fail
This
to reject.
is obvious, right? Yeah, fail to reject. Yeah. Okay, so now I think it is clear to everyone when we reject the null hypothesis based on p-value and alpha, and when we fail to reject null hypothesis. Yeah. Okay. So let's go over some more example. Okay, so we have one example here. This is actually this is about type 1 and type 2 error. So water samples are taken from water used for cooling as it is being discharged from a power plant into a river. So the water is discharging from power plant to a river. So it has been determined that as long as the mean temperature of the discharged water is at most 150 degree, there will be no negative effects on the river's ecosystem. So if the temperature is not above 150, then there will be no negative effects on the river's ecosystem. To investigate whether the plant is in compliance with regulations that prohibit mean discharge water temperature above 150. So we want to investigate whether the plant is in compliance with the regulations. Okay, so 50 water samples will be taken at randomly selected times and temperature of each sample recorded. So the sample size N is equals to 50. So the resulting data will be used to test the hypothesis. Okay, so here the mu is, the null hypothesis is mu is equals to 150. And we want to see whether the temperature is above 150 or not, right? If it is above 150, then it is dangerous for the ecosystem. It will negatively affects the river's ecosystem. Okay, so that is not good for the environment. Okay, so now we are not going to do the hypothesis test, but we'll determine the type 1 error, type 2 error, and we'll also determine which error is more serious and what should be our level of significance. Okay, so in the context of this situation, describe the type 1 error. So what is the type 1 error in this case? So when a type 1 error occurs based on a decision or based on your test. Okay, so I should recall the type 1 error. Type 1 means reject null when null is true. And type 2 is fail to reject null when we have evidence that alternative is true. Okay, so this is actually type 2. Yeah. Okay, so when a type 1 error will occur? In the context of the situation. Okay, so if we decide that the mean temperature is above 50 or the plant is not in compliance when they are actually not. So is it an error or is it a correct decisions? Our decision is if we reject null, so that's mean we are saying that the plant is not in compliance. That's when they are discharging the water with temperature more than 150 degree. So that's when they are not in compliance. Okay. So if our decision is, if we reject the null and actually they are discharging water with temperature above 150, is it a correct decision or any type of error? If our decision is the plant is discharging water above 150 degree when actually the temperature of the water is above 150 degree. Is it a correct decision or any type of error? Okay. Okay, so let me write down the statement. If our decision is that the plant is not in compliance, that's mean they are discharging water with temperature above 150 degree when actually they are discharging water with $150 degree. Okay. So what do you think? Is it a type or is it correct decision or any type of error? Yeah, this is correct decision, right? So there is no error. But if we say that if our decision is that the plant is not compliance when actually they are, discharging water less than 150 degree. So is it a correct decision or any type of error? Yeah, the first one was correct decision. Yeah, this is type 1 error, right? Because we are rejecting the null. We are saying that the plant is not in compliance. So that's when we are rejecting the null, right? Because null is the plant is in compliance. And alternative is the temperature is mean temperature is above 150 degrees. So that's mean they are not in compliance, the alternative. So we are supporting the alternative. If our decision is that the plant is not in compliance, that's when we are supporting the alternative when actually the null is true. So that's when we are making type 1 error, right? So this is the type 1 error. This is type 1. Okay, so now if our decision is, let's give you another situation. If our decision is the plant is not compliance, is compliance when okay, so what do you think about this statement? If our decision is that the plant is in compliance when actually they are discharging water with temperature less than 150, is it a correct decision or any type of error? Yeah, this is correct decision. You're right. Great. Okay, so if our decision is this, yes, it is correct answer. Yeah, it is correct decision. You're right. So now if our decision is that the plant is in compliance when actually they are discharging water with temperature above 150. So what do you think? This is type 2. Yes. This is type 2. This is not a correct decision. We are saying they are in compliance, but actually they are not. So what we are doing here actually, we are failed to reject null when alternative is true. So that's mean this is type 2 error. So this is type 2 error. So now which error is more serious in this case? Because actually we are concerned about the environment. We are concerned about the ecosystem of the river. So that's our main concern. So which error is more serious in this case? Type 1 or type 2? Which one is more serious? Okay, now you can see. Yeah, this is type 1, this is type 2. Which one is more serious? Yeah, you are right. Type 2 error is more serious because our main concern is the environment. So if our decision is the plant is compliance, but actually they are not. So that's mean we are saying they are compliance, but actually they are polluting the river, right? So that's mean type 2 error is more serious. So the alpha and beta value. So alpha is the probability of type 1 error. Alpha is the probability of type 1. And beta is the probability of type 2. Okay, so if you consider a small alpha, then your beta will be large if all the other values are fixed. And if you consider a small alpha, your beta will be. So I'm giving you
Yes, sir.
2, 3 scenarios.
I'm in class. The class is holding, it's still working. The class is still holding.
Okay, so I'm giving you 3 scenario. One is alpha is equals to 0.2 and beta is equals to 0.05. Alpha is equals to Okay, so I'm giving you two scenarios. Okay. So which one we should consider in this case? So when we'll be doing the hypothesis test, first you have to determine your alpha. So which alpha we should consider in this case? Anyone? So you want to do hypothesis test, and before doing the hypothesis test, you want to determine your alpha and beta. So which scenario we should consider in this case? 1 or 2? We should consider 2, right? Scenario 2. Because we do not want more type 2 error, because type 2 error is more serious. So we want the probability of type 2 error should be, we want to keep the probability of type 2 error lower, right? So that's mean we should consider a smaller beta and larger alpha. Yeah, you are right. Okay, so we have 7 more minutes, so I think we do not have enough time to start a new problem. Okay, so I'll stop here for today, and for your attendance, you should type present. And if you have any question, you can ask me, okay? And your second exam will cover chapter 4 to chapter 7. And I have already posted the practice problem for exam 2 on WebAssign. So you can log into WebAssign and you can start doing the practice problem. And your exam will be on April 8th. So before your exam, I think we'll have, how many classes we'll have? Let me check. So before your second test, we'll have 2 more classes. Okay, so next 2 classes will be review classes for exam 2. So I'll go over the review problems in the next 2 classes. So if you have any questions on the review problems, you can ask during the class time, okay? Or you can also email me. Any question? Yes, I'm going to post the note for chapter
It's-
8 on Blackboard right now. Okay.
It's in self-test we did a hypothesis test, t-test.
So in the second exam?